All right, 2.1 polynomial functions. Today I've got to show you how to do something on the graphing calculator that I'm sort of hoping you already remember how to do, because I don't have a graphing calculator to show you. Mine's dead, but I do have it on my phone. I have a document camera that I can show you, but it's missing, so I don't know where it went, which is unfortunate. Will I use this? I don't know. Okay, so our 3 learning targets for today. At the end of the day, I hope that you can classify a polynomial. If I give you something like 5x to the 0, can you tell me what the name of that is by degree? And can you tell me what the name of that is by the number of terms? That's my goal for today. Or if I give you something like 2x plus 1. By degree, by number of terms. That's the first one. The second one is, I hope that you'll be able to tell me the end behavior of any given polynomial if I give you the equation, if I give you the picture. And the last one is number of turning points and the intervals of increasing, decreasing. So those are our 3 today, 3 chunks. First thing though, we need to make sure we understand what standard form is. If I ask you to write a polynomial in standard form, what am I asking you to do? Simplify it, so what? Logan? Yep. So it's your polynomial with, you need notes. Yeah. It's your polynomial function with your largest exponents in front, and then it goes in decreasing order. This little chart can almost be broken up into 2 pieces. Split right here. So let's look at the first piece first. That 5x to the 0 power, that simplifies to just 5, and that's called a constant. A constant is when you have a degree 0. Anything to the degree 0 is 1, so it just cancels off. So you just have a 5. Just the variable, yep. So anytime it's just a number, it's just a constant. If it's a degree 1, so 2x to the first power would be a degree 1. That's called linear. If it's a squared, what's that called? It's like the topic of secondary 2. Quadratic, very good. If it's a 4th degree, if it's a 3rd degree, that's called a cubic or a cube. In secondary 2, hopefully you were taught those first 3 or 4. A 4th degree, a 5th degree are new this year. A 4th degree would look like this. And that is called a quartic. And then the 5th degree, guess? Quintic. Like that. So that's how I would classify them by degree. It has everything to do with that exponent. That's a really large highlighter. That leading exponent. You can also classify it by number of terms. So if it can't have 0 terms because then it's nothing. If it has 1 term, it's called a monomial. If it has 2 terms, it's called a binomial. And 3 terms would be trinomial. Everything past 3, we're just going to call it a polynomial with 4 terms, or just a polynomial is fine. If I give you a problem that can be simplified, you need to simplify it first before naming it. Otherwise, your name will be off. So, This little star thing probably should have come down here. But we care about the degree. We care about if it's a positive or negative. That's going to determine what the end behavior looks like. So let's just name number one, example one, and then we'll move on. On example one, if I were to write that in standard form, which term would come first? And then minus 2x squared minus 5x. Because it's a degree 5, we're going to say it's quintic. And there's 3 terms. Trinomial. Quintic trinomial. So for part B, writing that one in standard form, you would write 5x to the 4th minus 2x squared plus what? 8. And now we can name that one as quartic and trinomial. So simplify it if you can. Yes? The vocabulary is important because then I can talk about something that's a trinomial and you know what I'm talking about. What? You're not going to know? Well, okay, how about this one? We're learning the words because it's on the test and I was told to teach it to you. Okay, well, at least one of those 2 reasons should matter to you. Fair? I like reason number 1. However, if it's motivating for reason number 2, then use that motivation. Yeah, Diego?
Wait, why did it put minus 5 to plus 8?
Because I combined that subtract 5 with the 13.
Oh.
Yeah. No, good question. All right, moving on now that we all have a common goal. So, again, the degree affects the shape of the graph. And it's going to help you determine the number of turning points. Or where the graph changes direction. So I'm going to need maybe a little bit more room than down here. I don't know, maybe I won't. So what I'm about to write, this is where you'll write it. Sorry, sir, what? Well, my friend, let me show you. Okay, I want to look at first degree, second degree, third, fourth, and fifth degree polynomials. A first degree polynomial is always a line. TP stands for turning point. What's that? Thank you. How many turning points does a line have? None. Okay, a quadratic always looks like some sort of a U-type shape. Turning points, how many? 1, always. The cube function has 2 general shapes it could take. It could go up, go down, go back up, or that turn may never happen and it just slithers up. That wasn't very good. I'm trying again. So I have 2 options here. It either has 2 turning points or it doesn't have any. Is that okay? So what I'm trying to do right now is I'm trying to help you come up with a rule on if I give you an equation, how do I know how many turning points there are? And that's it. So what about x to the 4th? X to the 4th could either look like this, like a giant W, or it could look like a U. So how many turning points are there? Either 3 or 1. So now what I need you to do is come up with some sort of relationship between the degree and the number of turning points, or the maximum number of turning points. What do you notice? It's always 1 less, right? So the maximum number is 1 less. So without even looking at what a 5th degree looks like, what's the maximum number of turning points? And how do I figure out the other ones? 2 less than the maximum.
I'm so confused. When you say max number is 1 less.
So the maximum number of turning points is 1 less than the degree. So this one right here, it was degree 4.
Degree?
Yeah.
Oh, I thought you were talking about those two numbers. I was confused.
No. So the maximum number of turning points is always 1 less than the degree of the polynomial. Do you hear how many vocabulary words are right there? That's why we talked about the vocabulary at the beginning. So an x to the 5th could look like this, or it could look like this, or it could just slither up. And the shape of it is determined by imaginary solutions, I believe. So, and we're not going to talk imaginaries today, don't worry. But that's what goes, like, how do I know the difference between here and here? It's because of imaginaries. And if you remember, imaginaries come in pairs, right? So those turning points, that's why it goes down by 2, because imaginaries come in pairs. So now let's make sure you hit this learning target. If I gave you x to the 7th plus 6x to the 3rd, what would be the maximum number of turning points?
6.
Okay, would be 6. And then what would be the other possibilities?
4.
Okay, well, bingo. Let's go back. So here's the rule. If n is the highest degree, then the maximum number of turning points is determined by n minus 1. Is that the same thing that we said? It's 1 less. Good. If n is odd, then there are an even number of turning points. I don't know why we care. If n is even, then there has to be an odd number of turning points. It's always 1 less. So example 2, find the maximum number of turning points. That needs to be restated. We're just going to find the number of turning points. So I wish I could flag it, restate for next year. So turning points. We're only going to do 1. How many turning points, or what's the leading coefficient here? Good. So it's a 4th degree, which means there's either 3 or 1. And we'll just call it good. 3 or 1. With obviously the maximum number being 3. I'm assuming that you know 3 is bigger than 1. We're good there, so you don't have to specify. I think we're good. Yes? Nope, it's just that first term. Yep. So we're only determining it by that leading term if I were to write it in standard form. The rest of this garbage, that's what's going to determine if the shape is this shape or that shape. That's what affects everything else. But
You shouldn't even do this garbage.
Hey now.
Stupid.
Hey, I never said that. Okay, so now we're going to talk end behavior. Notice when I'm saying end behavior, I'm going to go back to these sketches right here. When I'm talking end behavior, I'm talking about what's happening on this end and what's happening on this end. The stuff in the middle doesn't matter. What do you notice about all of my odd functions?
There's one going up and one going down.
Yeah, they're going in opposite directions, right? So the odd functions go in opposite directions. The even functions, they go in the same direction. Now, the positivity of it comes with that leading term. So I'm going to say if this is a 4x to the 3rd, it is a negative odd because the leading term is negative, the exponent is odd. Is that fair? And then again, the rest of the garbage after that doesn't matter. This starts, I'll say that a lot. I call it, stuff, garbage, whatever. So if I'm looking at a positive even function, I know that both ends are going up and both ends are going together. They go up because it's positive. They go together because it's even. Which means if it were a negative even function, they would be going together still, but what? Yeah. Good. And you told me that the odd functions go opposite directions. If it's positive, as time goes, it should be going up. And again, I don't know what's happening in the middle. It could be like this. But that would be an odd function because they're going in opposite directions. Fair? And then a negative odd would look like what? Starting up, going down. Yep. Now there's two ways to state end behavior. One is easy, one is very mathy. So when they're going up together, we're going to call this an up and up. So on one end, the left end is going up, the second end is going up, so up and up. Which means part B, the negative even would be called a what and what? A down and down. The other part B, where it's positive odd, it would be down and up, good. And then the part D, so while I'm starring typos, there's my next one. Okay. Formally, how do I state that? Mathematics is very precise. So I don't remember seeing a lot of like, what are these symbols and what do they mean until I got to some of my college classes. This is what this means. For an up and up, it looks like this is the basic shape. If I were drawing that maybe a little bit bigger, it might be easier to see. So, as x is going negative, imagine like a little tick mark. Y is approaching what infinity right here? That would be a positive infinity. So this is what these little symbols mean. As x, this one right here stands for approaches. If you can read that, just know that that says approaches. Negative infinity. Y approaches, what's happening? Positive infinity. That's the up part, right? So anytime it's an up, it's with positive infinity. As x approaches positive infinity, so as x is going this way, what's y doing? Going up again to positive infinity. That's the up part. The thing that's kind of nice about this is this entire section, don't do that with highlighter. This entire section is the same for all four cases. You just need to match the ups with the infinities and the downs with the negative infinity. So let's look at a down and down. So the shape would look like this. So it's going to match your down and down. Again, those are the same. So as x approaches negative infinity, so as x is going this way, y is doing what? Going to negative infinity. As x goes to positive infinity, y is going where? To negative infinity again. You'll have the opportunity to practice this about 7 times on your assignment tonight. Which is better than 12. You're welcome. Good. So it's just fast, and if it makes you, no, it probably won't. I've already done the assignment, or most of it, so. Okay, what about the down and up? Down and up looks something like this. So as x approaches negative infinity, y approaches negative infinity. As y approaches infinity, or just kidding, as x approaches infinity, y is approaching infinity. This is your down and up scenario, which is what it says here. And fill in that last one. If it was up and down, what would those two blanks be? Infinity and negative infinity. So you have to be able to do that based on an equation and based on a graph. Yes. Well, if I'm giving you an equation or a graph like this, it's just like, just imagine like as x, you just make it as x goes this way, y goes that way. As x goes this way, what? I don't know if that answers. What do you mean? How do I know if it's x or y? So it's like you see like, is that okay? Okay. Thank you. All right, so again, you need to be able to do that based on a graph and based on an equation. So for part A here, make sure everything's in combined. If you were to rewrite that in standard form, what would it look like? Or which term would be first, I guess? That's all we care about. The 5x to the 4. So what you need to know is that it's positive and it's even, right? So on my homework, I wrote plus and then even, and then I even like sketched the picture briefly so that I remembered it was an up and up. Because it's positive even. So they're going together and they're going up because it's positive. So again, the first chunk is exactly the same. As x approaches negative infinity, y approaches something. As x approaches infinity, y approaches something. So it starts like that every single time. Again, it's positive even, so it's up and up. what do we put in these two somethings? Both of them are what? Infinity. So let's make sure you got it. On part B, sometimes I like to jump ahead. Are we good? On part B, make sure you know what that first term is. Decide if it's up and up, down and down, down, up, whatever. And then try writing that formal behavior. Really quick, what time do we get out of here? 11:01. Okay. Okay, so roughly around 11. Okay. Okay. Well, if you're wrong. Okay, so is this up, down, up? This one is negative odd. So it slithers like that. So it is an up, down, right? So negative odd because of this term right here. So how does it look? As x approaches negative infinity, y approaches, we're going to say up. How do you say that? Infinity. Infinity, y approaches negative infinity. Okay, did you get it? Any questions? Are you bored? Don't be bored. Let's move on. No, let's move on. So let's do, this is my last thing. Can we put it all together? Let's do formal or the end behavior one more time and then we'll skip it for the rest. Here's our picture. So this is looking at the ends. Come on, sweetie, what's happening here? Hello, where are you? I don't want that. Okay, this is an up and up. So fill that in. Now, when I say turning points, I don't want to know how many there are. If I wanted to know how many there are, I would have asked for the number of turning points, but I didn't. So turning points, I need to actually figure out where the turning points are. So in this case, it turns where? At 4, 2. And the increasing, decreasing intervals historically have been the ones that you make the biggest mistake on. What I'm really asking here is for what values in the domain we're going to do it in interval notation. So, but yeah, something like that. That's any. Pointing back to them again. Yeah. Yes. That was inequality notation because you're using inequality signs. We're going to do it in like, that's very similar to interval notation except for it's a point. Okay, so when I'm asking you for increasing, decreasing, I'm asking you for what values in the domain will my graph be going up and down? Now, when I'm talking about the domain, am I talking about the x values or the y values? Talking about the x values. So make sure you list everything right here using the x values. The increasing, decreasing, that has to do with the y values. So here's how I like to do it. I like to draw a line on my turning point. And it circles the number that will be used in the increasing, decreasing intervals. In this case, the number is 4. So I don't care that it's turning at when y is 2. I don't care that minimum value is 2. Sorry, I started to stutter again. I care that it's happening at 4 because that's on the domain where it's turning. On the domain, this is where positive infinity is. On the domain, this is where negative infinity is. So I've broken the graph into 2 chunks. On this chunk, is my graph going up or is it going down? So if you're like on that roller coaster, my graph would be decreasing, right? And on this part of the domain, my graph would be doing what? Increasing. So now we just have to write that below. The numbers that you wrote right here are the intervals of increasing, decreasing. Now, what do we do with the 4? At 4, is my graph increasing or decreasing? It's neither, so we're going to call that constant. So at 4, it's constant, it's flat, and that has a lot to do with calculus. So you're not going to use a bracket because it's not included into either group. So it is increasing from what to what? 4 to infinity. And it is decreasing from negative infinity to 4. Likewise, let's do this next one. We're not going to worry about end behavior because we've done that several times. Is that okay? Let's just do those last 3. So again, where are the turning points? At -2 and 2, -8. Right? So -2, 0, and 2, -8. All right. It's increasing here and here, decreasing there. So, negative infinity, it turns at -2, it turns again at +2, and then it goes forever to infinity. So it is increasing. I'm just going to write it on the side. It is increasing from where to where? Negative infinity to -2. Make sure the smaller of the two comes first. And then it changes direction. It decreases from -2 to +2. That's 2 2's. And then it turns again and it increases from 2 to infinity. And there's a symbol that you can put in between those two intervals. It's a little U that combines those sets together. So what I'm saying is that my graph is increasing every point between negative infinity to -2, and then from 2 to infinity. You're going to have to use the restroom if you need blurriness. Yes, you need that. Okay, and that's it for that one, right? Now, the last 2 examples, the last 2 examples don't have the graph provided, so you have to do it based on the equation. We should be able to do end behavior based on the equation, but I really don't care. I think you've got that down. Let's just look for turning points. Now, remind me, who are my Casio people? Okay. Play with it. We should have time to look at your calculator today. See if you can remember from last year. Okay, so for everyone else, is it okay if I sit here?
Oh yeah, totally.
For everyone else, up on the top left corner, there's a Y1 button. You will plug in your function. Again, remember, I'm sorry, I don't have a calculator. I think I can download one on here. I'll work on that.
It takes a long time to load and it doesn't work on most devices.
Good to know. If you, doesn't matter. So, from there, you want to check your window. On the window, it should have an X min, an X max, a scale, a Y min. It might have something else, a Y max, and then scale. The standard window is from -10 to +10. The scale just refers to what each tick mark is worth, so 1 is sufficient. -10, +10, 1. No, I don't ever really change scale. It doesn't matter to me. But if you ever zoom out and you have, if it was from -100 to +100 and the scale was still 1, that bar in the middle would look like this solid line, right? Because it's trying to fit 100 tick marks in between. Yeah. So if that's the case and you care, you could change it to a 10. But if you change these to 100, you won't see the graph itself. After that, on the far right, you're ready to graph it. And your graph should look something like this-ish. I figure if you put ish by things, it just takes care of all mistakes. We need to know the turning point, meaning we need to know, on your test, just put ish. I think it's about 5-ish. Okay, yeah. You'll get it right-ish. There you go. Rightish. So we're trying to find turning points. Really quick, does anybody have a hard time graphing that and seeing the graph that looks mostly like this? Yours, no. I don't know where my charger is or my document camera. We're fine. Okay, so now I need to find that turning point. Next to the graph button, there's a trace button. Nope, don't write in highlighter. There's a trace button. And above the trace button, there's a calc function. Do you see it? So if you push second calc, it leaves you a bunch of choices. 0 is 1. And the one that you're going to choose is what? That is a minimum value, right? The turning point's a minimum there, so we want to choose minimum. Now when you choose that option, and I'm sorry I can't show you, I can show you one-on-one if you're struggling. When you choose that minimum function, it asks you for a left bound, right? And then it gives you this little like Spider-Man looking cursor thing. You have to scroll that spider cursor thing far enough to the left so it's to the left of the minimum. The calculator just wants you to give it a piece of the domain where to look for that lowest value. So if you scroll that little cursor to the left so it's clearly left of the minimum and push enter, then it will ask you for a right bound. So for the right bound, what do? Scroll to the right, give it another bound, and push enter again. It will ask you to guess. You don't ever have to guess unless you're way far away from that minimum value, so just push enter again. And it tells you the minimum value is what? 1, 2. Anybody have, did you already know this? Did I just waste your time? Is this helpful? Thanks, Logan. You already knew it. I just wasted your time? Okay, well, you're welcome. There you go. So how does that help us in the problem? Let's go back over here. Well, first of all, sketch it-ish. We know 1, 2 is the minimum. You may want to get 1 or 2 other points in there. You can use that using the trace function. I actually don't care a whole lot right now because we're out of time, but for the homework. So do you know how to find other points on your graph? You just, okay. So you just click the trace button, and if you type in 0, enter, at the very bottom it should tell you the point 0 what? It's probably 0, 3, so you know a point's there and a point's there because they're symmetrical, right? If you put in a -1, it would tell you what? 6? Yeah, I don't know why I'm putting equal signs because they're points. So I know that this should have been right here, and then that would have given me a better. That's just a whole lot of ugly right now. Let's try again. You know what? Okay, moving on. So turning points happened at 1, 2. And then, are you okay with increasing, decreasing? Mm-hmm. Okay, well, it is almost 11-ish. So we, please start your homework with this explain, justify, defend question. It's 2 parts. And then I've got to teach you the cool trick and we're done. We don't have time to do the explain, justify, defend question together. This one was answered. I wrote it on my presentation. Number 2, just say something about the shape. Because really, the reason we do all of this is because we want to know the general shape of the graph. So if you say that in sentence form, then you will get on the right track. And if you need to talk about 1 and 2, then let me know and we can talk about those on a later date and time. I just want to show you the cool trick. If I'm given an input-output or an XY chart, I can tell you with relative ease if this is a linear function, a quadratic function, or a cube function, or something else. And the way you do that is finding the differences from term to term. The first thing you want to look at is just to make sure that these are going in the same order. So it's not like I went from -3 to 0 and then to 1. Like they need to be, the common difference be about the same. So, yes, that would be fine. Excuse me. Then what you do, and this is my last problem, Logan, and then you can fill out. So you're going to find, if you're sitting at -10, jump to -1, you went up by how many? 9. And then from -1 to 0, you went up 1. From 0 to -1, you went back down. And then to 2, up 3, and then up 12. If that line of numbers were all the same, I would say that it's linear because it took me one iteration to figure out that all 5 of those numbers are the same. They're not the same, so let's do it again. So from 9 to 1, we went down 8. Nope, hold on. I can do hard things. Give me a second. Okay, so this would be down 8. This would be down 2. This would be up 4. And this would be, hold on, 9. Give me 1 second. I'm panicked. Did we screw up somewhere?
Yeah.
Supposed to be a 13? So this would make this a 10. Be very careful. If you make one little tiny mistake, then everything gets thrown off. All right, so is it a quadratic? Because if these were all the same, then yes, it would be a quadratic. They're not, so you do it again, and you just keep going until they're all the same. But this one would be up 6. This one would be up 6. That's a 10. This one would be up 6. These are all the same. And because it took me 3 times doing that to get there, I can say that this function represents a cubic function. So it's the degree, not the number of terms. I had a kid that we'd have to like calm him down every time those 3 numbers came up together. And he'd point them out every single time and be like, it's okay, Brandon, just like, we're fine. And every day I'm like, well, there's the number again, sorry.
My brother bought like a certain amount of food and it ended up being $6.66. So I'm like, don't buy that.
Yeah, no, that's going to give you a food poisoning.
Yep.
Okay, cool. How do you feel about it? Do we feel like we hit all of our learning targets? Do you want to go back and talk about the explain,
No.
justify, defend since you have to do it anyway?
Yes, that. I want to do that.
This kid, man. Okay, cool.
He can just not listen.
That's true.
I don't listen a lot, but listen.
Wait, we're going to be doing 5. Yeah. Try it. When identifying intervals on which the graph is increasing or decreasing, so keywords, should you use the x or the y values? If you don't remember, go back to where we talked about increasing, decreasing. Hopefully you wrote it down. You should use which values? Why? Because, yeah, that's part of the domain.
What's the y
Range. It's on the scorecard as its own column, the 5 points. Yep. You're looking for the parts of the domain. And then do something like that. And then what does knowing where the graph is increasing or decreasing and its end behavior do for us? It gives us the basic shape of the graph. Yeah. Yep. If you wanted to write a rule like for this, like it takes however many times, I don't know. The rule for the bottom, I don't know.
Just do what you did.
If you want to write it, you can. If you want to say see example, you can do that too.
Oh,
My first year I taught this subject, I was like, well, it's cool, which is why I called it a cool trick, but that's kind of silly. I don't know if you'll ever use it again, so I didn't teach it. I was like, that's kind of stupid. I don't care about that. All right, today is the first time that you have additional problems in your worksheet. So you know this answer Can I borrow the big scissor right there? I just put things around the front of the I'm sorry. So this answer key that you have, that front page where it had additional problems, make a better door than a window. There's 5 problems right here on the front of that page that you have to do first, and then you work on the bookwork. Or you can do it last. I mean, be a rebel, whatever you want.
No, I am a rebel.
I can tell. All right, cool. Now I'm going to awkwardly sign off to my recording. If anybody ever watches these, I don't know if they will, but if you're absent, maybe they'll be useful. It's not as good as the live show, but thanks for watching and peace out.